Okay, so we got a normal week this week. The stuff we did on Monday, that online homework is already posted, and then I'll add a second one due Sunday. So there'll be two. It'll be in two separate sets this week. There'll be two separate sets due Sunday night. The one that's already open, and then the one of this set. Okay, so this is the first part of chapter 12, which is chi-squared distribution. So we've dealt a lot with the normal distribution, but not all things are normally distributed. Okay, so like think about like the number of people in line, say at a coffee shop. Okay, so what would that distribution look like? The number of people in line at a coffee shop. So if this is, first of all, what's the least that could be? Yeah, so you could have 0, right? But you wouldn't have a negative. Okay, and suppose the place doesn't get much business. Okay, they don't get much business. Then what would the frequency? So there's a number of people in line. What would the frequency distribution look like if this doesn't get much business? This coffee shop doesn't get much business. So I'm going to draw some curve up here. Okay, I'm going to draw some curve. That's our frequency distribution curve. What would it look like? Left skewed. Right skewed. Something else. Left skewed, right skewed. What do you think? So this you wouldn't have. This is the least you would. What's that? Right skewed, right? So it might be something like this. Or even more just drastic here. There we go. That's better. Okay, most of the time there's 0, 1, or 2 people in line, but sometimes there's 3, 4, and 5. It's right skewed, right? Because the median's around 1 person in line. Okay, but because sometimes there's 3, 4, 5, maybe occasionally 6 people in line, that pulls the mean out to the right, right? That's so most, the median, the center of the data around 1, but right skewed. Okay. Also, you can think about like the number of, at the end of baseball games, the number of runs scored would be something also like this, right? So lots of times in baseball games, a team will get 0, 1, 2, or 3 runs often. But then sometimes they run up a high score, 4, 5, 6, 7, 8 runs in a game. So number of runs scored in a baseball game would also be like this. So this is kind of what the chi-square distribution models, things like this. Right skew, so 0 is the minimum value of the variable, and you have a right skewed distribution. That's chi-square. So and so then you have different there's actually many different chi-square curves, and it goes to degrees of freedom. So here is showing you 3 different versions. 5 degrees of freedom is the blue one, 10 degrees of freedom is the green one, and then 19 is the gold one. And what do you notice with more degrees of freedom? Yeah. So when you have more and more degrees of freedom, it's like becoming normal, okay? Becoming normal. All right, so here's some properties of the chi-square curve. The total area under the curve is 1, just like the normal distribution, okay? Just like the normal distribution, and then the areas represent percentages or probabilities. Okay, and then a chi-square, it starts at 0 and extends indefinitely to the right, approaching but never touching the horizontal axis. That's similar to our normal distribution, but normal distribution, it's on both sides, right? Both sides, it does that. Okay, it's right skewed, we talked about that. And as the number of degrees of freedom becomes larger, the curve becomes increasingly more normal. Okay. So this is just the kind of the nature of the chi-square curve and the basic properties. Okay, so we're not, the first thing we're going to use chi-square for is what's called goodness of fit test. So the examples I gave about number in line and number of runs in a baseball game, we're going to be doing something a little bit different than that. We're not going to be looking at variables like that, but we're going to be doing what's called goodness of fit. So let's see what that's about. Okay, so here's a table of expected frequencies of last year's violent crime distribution based on the 2000 distribution and 500 total crimes committed. So they looked at the distribution of these violent crimes in 2000, and then they said, if in another year there were a total of 500 crimes, what would we expect based on 2000? Well, we'd expect this many of each of these, okay? So they took the relative frequencies in 2000 and they said, okay, if there were, in another year, if there were 500 total, how many total of each would there be? Okay, does that make sense? So here's that same thing again, right here. This is the expected based on the year 2000. So based on the year 2000 and 500 total crimes, this would be the distribution of those 4 different violent crimes. This is what they actually observed in some later year after 2000, say 2011. And this is based on 2000. Okay, so what we're gonna do is we're gonna see, does the observed in 2011, does it match up with 2000? Does it fit? All right, so that's what we're gonna test. We're testing to see, did the distribution stay the same, or is it significantly different? Right, so we're gonna do a hypothesis test to see if our observation distribution, do we have evidence that this the observed distribution in 2011 is significantly different than what we had in 2000? So the way we do that is we compute this variable right here called, this is our chi-square variable, which looks at the differences, right? So we're going to total up, it's like we're totaling up the difference between the individual, the distribution of the individual possibilities here. So we've got the O minus E for each of these, and then we're going to square that, and then we're going to sum, and then we're going to divide by the expected and sum those up. So this is our test statistic. So you see that as these become further apart, as O and E are further apart, this number will be greater, right? Because these differences will be bigger, and you'll square them, and then divide by E, and then add them up. So the more that the O and the E are apart from each other, the bigger these numbers are in magnitude, and the bigger this number is. So the larger this number is saying there's more and more possibility that the 2 distributions are different. The smaller this number is more suggesting that the distributions are the same. Does it make sense?
What is the chi-square number on a graph? What is it?
So it can be used. So the chi-square can model different things. So this is one thing that it can model. This test statistic of this number is going to be what our variable for chi-squared, what we're going to use for goodness of fit. So yeah, so this number is going to be like our x-axis. But it can model other things too, like the number of people in line or runs scored in a baseball game. Does that make sense? So, but we're going to use it. We're going to use chi-squared for this. Okay. So then, let's see here. So let's go. Let's talk about the goodness of fit test, and we'll go back and finish that one about the violent crime. All right. So to perform a hypothesis test for the distribution of variable for the chi-square goodness of fitness test, we have some things that have to be true first. So all of our expected frequencies are 1 or greater. Okay. You can't have 0 for any of the frequencies. Okay. At most 20% of the expected frequencies are less than 5. And then you have a simple random sample. Okay, so our expected frequencies, all of them are 1 or greater, and 20% of them, at most 20%, are less than 5. Those are the two things we have to check in order to use the goodness of fit test. Okay, so we're going to do a hypothesis test, like I said. The null hypothesis will be that the variable has the specified distribution, or what we observed is the same distribution as what we expected from past, for whatever, okay? Meaning, in the past screen, like O and E are the same, okay? Our observation and our expected are the same, and then the alternative was they're not the same. Okay, so we're going to have a significance level, like before, and then we're going to compute, this is the chi-square statistic, this is what I just showed you, and that this was the last row in the table. For each frequency, we did that, and then we added them up. Remember, this symbol means add, sum up. We're going to sum up all those. So where O and E represent the observed and expected frequencies, and then denote the value of the test statistic, chi-square, chi-naught square. So the test statistic is chi-naught squared. Okay, so that's our, let's go back. So let's go back and look at this one, and let's do a we need a significant. So let's see. Does this meet the criteria? So remember, each one of these has to have a frequency greater than 0, and then at most 20% less than 5. Right? So how are we doing? So we're looking at our expected frequencies. Do we meet both criteria? Right. So there's none that have 0. And this one is actually greater than 5. It's 5.5. So we are okay. What? Wait. Yeah. Okay. So they're all 1 or greater. And all of them are greater than 5, so we're in good shape there. We can do it. So now we need a significance level. So let's let's look at say 1%. So we need a new chart. We need a new chart, and that's the chi-square distribution chart. Where is that? There it is. Okay, so here's chi-square. And you see that you have the degrees of freedom over here. Okay, and then you have the different alpha significance levels here. So 10%, 5%, 2.5%, 1%, and 0.5%. Okay, so the degrees of freedom then is one less than the number of frequencies in your distribution. So that number is called C. In this problem, C equals 4. There are 4 different frequencies in the distribution. So then the degrees of freedom is 3. So we have 3 degrees of freedom, and we're looking at a 1% significance level. And we're going to get our critical value. Okay, so if C equals 3, 1%, 11.345. Okay, so let's change it to 10%. So I'm going to change it to 10% significance level. Okay, so at a 10% significance level, with 3 degrees of freedom, we have 6.251. So let's make a little drawing here. So our critical value is 6.251, which leaves an area here of 10% with 3 degrees of freedom. So, and remember what that significance level was. We talked about it when we first started talking about it, but it's probably slipped away what that means. That was the probability of a type 1 error. So meaning if our test statistic falls in that range, then and then we reject the null hypothesis, this means there's a 10% chance that we're incorrectly rejecting, right? That we just happen to get a really big sample, and there really isn't evidence to reject the null hypothesis, but we are. So that's what the significance level is, right? It's the probability of a type 1 error that we shouldn't have rejected, but we did. Okay, so that's what that means, if you remember. Okay, and so then where is our chi-square test statistic? Is here at 3.555. So reject or no reject? We don't reject, right? So this is our rejection region here. And this is our non-rejection region. And so what's our conclusion? We have evidence or we don't? We don't have evidence that the distribution in 2011 is a different distribution of crime than our expected, which we based on 2000. So we don't have significant evidence to say, hey, look, the relative frequency has changed a lot since 2000. Okay, any questions on that? So that's basically it. We can spend the rest of the time working on examples. Okay, so let's do one more example together, and then I'll give you some. Okay, any questions? So again, the chi-square distribution it can model different things, but this is a very specific thing that we're using it for here in the goodness of fit test, is to test whether two distributions are the same or not. Okay, and then we'll see that we'll do some by hand. Some that have less frequencies, we'll do by hand, and then when it gets a little bit more work, then I'll show you how what's it called? What's it called? Stat crunch. We'll do it by stat crunch. So this first one, let's do this one by hand. So observed frequency. So first of all, we need to get the number of observations. So here's our observed frequencies. So how are we going to get the total number of observations? Should be easy. What are we going to do? Add them up. Okay, we're going to add up all the individual frequencies of the different outcomes. Okay, and so if we add those up, it looks to me like, is it 500? So I think that's 300, and that's another 200, so I think we got n equals 500. So based on 500 observations, we need to find out what our expected frequencies are. How are we going to do that? So this is the relative frequency. So this is outcome number 1, outcome number 2, outcome number 3. So if outcome number 1 has a relative frequency of 0.2, then how many times do we expect it to happen out of 500 observations? How would we find that? So it has a relative frequency of 0.2. And so then in 500 trials, how many times would we expect outcome 1 to occur? Or how would we find that? Do you remember what a relative frequency was? It's a relative frequency. It's like a portion, right? Or a percent as a decimal, right? So in 500 total observations, our relative frequency is 0.2. Yeah, you're going to multiply. So we want 0.2 of 500, right? Or 20% of 500. So I think that's 100. So so for number 1, so that we'll just write them down here. 100. And then 0.4 is going to be for 500, 40% of 500, or 0.4 times 500. 200. 0.3. It's going to split the difference, right? 150. And then 0.1. 50. So for our 4 different outcomes, column 1, 2, 3, and 4, based on the relative frequencies and a sample size, total sample size of 500, this is what we'd expect. Okay? What did we actually observe? Here's what we actually observed. With a simple random sample, we actually observed 85, 215, 130, and 70. And what we're testing is our null hypothesis will be the distribution based on observed frequencies is not significantly different than what we expected, right? Or the alternate hypothesis would be, oh, it's different than we expected, right? These frequencies are deviating significantly from what we expected. Okay, so how do we do that? We do O minus E. So let's do that. So minus 15, plus 15, minus 20, plus 20. And then we square those. 225, 225, 400, 400. Then we divide each of those by E. So check my math here, 2.25. What would that be? That would be 1.125. I don't know, what is that? 4 over 1.5 would be, help me out, 2 point something. 6, 7. And then this one is 8, right? Did I do the math right? Okay, and then we add those up. And so we got, I don't want to do this in my head. As soon as you get it, shout it out. 14.045. So this is our test statistic for the goodness of fit test. It's an indicator of the observed distribution being different than the expected. The bigger that number is, right, the bigger these numbers are, the bigger O deviates from E, the bigger that total will be, and the more likely that they're different. So we're going to look at the 5% significance level, and how many degrees of freedom will we have? Again, 3 degrees of freedom, 1 less than the number of outcomes. So we go over here to the chi-square table. 7.815. So we'll make a little sketch. So our test statistic was, our critical value was like 7, did I say 7.8? Okay, so over here is our rejection region. Right, we said the bigger this number gets, the more likely the frequencies are different. Okay? And so we're going to reject, if it's our critical value, then it's 7.8. So at a 5% significance level, if we exceed 7.8, we're saying, look, there's some evidence here that the distributions are different, and if it's less than, we're not going to reject. So, what do you think? Are we going to reject or not reject? We're going to reject because our test statistic is here at 14.045, indicating what? We have evidence or we don't have evidence? We have evidence of what? That what? Right, that what we observed in terms of the frequencies in this distribution is significantly different, okay, than what we expected. Okay, and remember this 5% means so right here at 7.8, we're saying, if it were 7.8, we're saying there's a 5% chance that we would reject incorrectly. We would reject incorrectly, okay, at 7.8. So the p-value, the p-value then would be based on our test statistic, right? So this area here, this probability, would be the probability that at 14 we would incorrectly reject. So can we kind of see what 14 is? 3 degrees of freedom. So with 3 degrees of freedom, notice here for this number right here is still not quite 14. So, and what p-value is that? The p-value for 12.838 is 0.5%. Or 0.000005. Okay? So what does that mean? So at our test statistic of 14, there's less than, because 14 is greater than 12.838, there's less than a 0.5% chance that we have rejected incorrectly. Okay? So the 14 corresponds to a p-value would be something, here's our 3 degrees of freedom, it would be less than 0.5%. So we can be very, very confident that we've rejected correctly here, okay? Because only less than half the percent of the time would we make a type 1 error in this case, meaning we rejected and we shouldn't have, okay? Any questions on this example? Okay, so why don't you try, I'll leave this up here, so write down, or try 12.22, and so I don't have the blue sheets for you, if you could use your own paper, but please give me a clean left edge. If you're tearing out of a spiral, give me a clean left edge, please. Okay, so you got everything you need there? You're going to do 12.22. You're going to build the table, and then here's the chi-square chart, and you're going to see if our observed frequencies, we're testing to see if our observed frequencies are significantly different than what's given the distribution. You can work together, okay? I'll be right back. Can we go on? Is everyone done? No objections? All right, so let's look at I think you can do it. So here's this is U.S. population by region. Okay, U.S. population by region: Northeast, Midwest, South, and West. And then it said a simple random sample gave these values. We're going to identify the population and variable under consideration. At the 5% significant level, do the data provide sufficient evidence to conclude that this year's resident population distribution by region has changed from the 2000? So this is year 2000. Here's the results of our simple random sample. Okay, so let's do AA together. What's the population that we're looking at? What would the population be? So not that's the size of the population. So is that was this? That's the sample size. Okay, so 250 is the sample size. What's the population? Meaning what total group are we investigating?
U.S. residents?
Yeah, U.S. residents. And then what variable do we have? So U.S. residents is our population, and our variable that we're looking at is region, right? So the variable is region, and the population is U.S. residents. Okay, and we want to do it. We're doing a chi-square goodness of fit test to see if our random sample is suggesting that this distribution is true or something's changed, right? Something's changed. Okay, let's do it for your sheet. I think you got what you need. I need to. So you can build a table, and then I'll show you the chi-square chart in a second. Okay, anybody have a question? so that's your critical value. Or the greater this is, the more indication that these are different. So where's your reject region? Is it to the right or to the left? To the right, right? Because if you get critical value, then anything greater than that is indicating these are different. Okay, I'll put the chart up now. Last chance for questions on this one. Are we okay? Are we good? Okay, so here's kind of a cool example. So M&M's does research in terms of what percentage of the colors in a bag will generate the most sales, right? So it's not just, they just don't randomly throw the colors in there. They specifically try for a certain proportion of colors because somehow by changing the proportion of colors, it affects their sales. So they're trying to maximize that. So here is claimed percentages by the company. Brown 30%, yellow 20, and red is 20, and then orange, green, and blue 10. Okay, so here are the counts. So someone get 3 bags of M&Ms and they counted. Okay, they counted up all the M&Ms, and they did this. And so at the 2.5% significance level, is there reason to believe that the proportion of colors is not what the company claims? Okay. So let's do this with StatCrunch. I hope I can get this to work. So rather than build that whole table, we can just put these numbers in, and it will just like that, it'll give us the test statistic rather than building that table that we've practiced now a couple times. So let's see if I can make that happen. We can do that together. In the homework, you have that little button, right? So it gives you the data, and then you see that there's a teeny little button that you just click, and it just takes you right to StatCrunch with that data. But for this one, we're going to have to put it in ourselves. Okay, so let me show you that first. Oh, it's here. Okay, so remember while I'm getting there that this Sunday's homework, it comes in 2 different sets. You're going to have to, like the one that's already posted, and I'm going to post a separate set for Chapter 12, okay? Don't forget that. All right, so let's find one here. Let's try number 4, see what that does. Okay, so here, this is your number 4. It says, a researcher drilled a hole in a die, filled it with a lead weight, proceeded to roll it 191 times. Okay, observed frequencies are 1, 2, 3, 4, 5, yada, 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 5% significance level. And if you see this little thing right there, that will take this data and open up StatCrunch and put that data in StatCrunch. Okay, so here are the different outcomes, and here are the frequencies. Okay, so the frequency of rolling a 1, frequency of rolling a 2, etc. So let's see here. I want a different one. This is because we're going to do that in a second. I want a different one here. Oh. Here's the M&M's problem. So let's see what happens when it opens up. Okay, so the percentage then would be expected, right? So this would be our expected percentages, and then the frequency, this would be our sample. This would be our observed. So if you go to stat, and you go to goodness of fit, okay, so everyone pay attention here. You're going to go to stat, goodness of fit, chi-square test. And then you have to tell it, so observed. So which one is our observed? Our observed is frequency, right? This was from our sample, what we observed. And then expected is percentage column. All right? So in some situations, what's expected is that all of them have the same percentage of occurrence, that you expect all of them to occur equally. So if that's the case, you don't need this column, and you just have all cells in equal proportion. Does that make sense? That you're expecting all of them to be equal, uniform distribution. Okay? But in this case, they're different, and all the ones we've done so far, they're different. Okay? And then you don't need any of this. So you just make sure you get the right column for your observed and your percentage, and then compute. And then it gives you the chi-square variable and the p-value. All right, and degrees of freedom. Okay? And the sample size, right? So it gave you the sample size, degrees of freedom, that chi-square test statistic that we were computing, and then the corresponding p-value. So let's see if we can do this from scratch here. On the one that I gave you, or let's go on to a different one here. And let's just use this one. Okay. So let's actually do this for the M&Ms. Where is it now? Is it here? Okay, so for M&Ms, green, 10%. Orange, 10. Yellow, 20. Blue, 10. Red, 20. And brown, 30. Okay, and then our observation, how many greens did we observe? 43. Orange, 51. Yellow, 114. Blue, 43. Red, 106. And brown, 152. Okay, so there's our data. And so again, stat, goodness of fit, chi-square, which is our observed column. Yeah, so, and then if you just open up StatCrunch, so this came from that problem that had the same setup. But if you just open StatCrunch with nothing in it and you're typing stuff in, so then you would select like variable 1 or variable 2, right? The names of the columns will just be like VAR 1, 2, 3, 4, and so that's what you would select here, okay? But this one's been already set up for this problem, so frequency is observed, expected is percentage, and here we go. So for this particular example, chi-square is 4.09. Everyone write that down. The p-value is 0.536. So our test statistic, chi-square naught, is 4.091. P-value is 0.5364. And we want to, at the 2.5% significance level, we've got how many degrees of freedom? 5, because there's 6 outcomes. 2.5% is here. 12.833. Critical value, 12.8. Test statistic, 4. Conclusion, we have evidence or we don't have evidence? We don't have evidence that the distribution is different than what they're claiming, okay? So there's a real strong case that what's actually happening in practice is the same as what they're claiming the percentages are based on this sample, okay? So based on this sample that we took of 3 bags, we would not say that they're incorrectly claiming what the proportions are. Okay, what does this p-value mean? So this p-value corresponds to this number 4.091, and so basically we're saying if we were to reject, there'd be a 53% chance that we were wrong, right? If we were to reject at this particular test statistic, there would be 53% chance that we shouldn't have rejected. So we're definitely not going to reject here, right? That makes sense. But this is so much less than 12.8. We're not even close to rejecting this. And if we did, there's a 53% chance we'd be wrong, okay? All right, so then the last thing is rigged games, okay? So the goodness fit test is a way of testing rigged games. So for instance, in roulette, there's 3 possible colors you can get. You can get red, black, and green. And on the wheel, there's 18 red, 18 black, and 2 green. Okay? So the first thing we need to do is get what are the relative frequencies? How would we get the relative frequency of red? If there's 18 red, 18 black, and 2 green, how would we get the relative frequency of red? Divided by? Not 200. It would be the total number of possibilities. Would be 38, right? Well, we're just developing the relative frequencies. We haven't gotten there yet. So this is just the relative frequencies. So what's 18 over 38? Okay, so 0.47 we would expect for red, and same for black. And then this is our expected relative frequencies. And then for green, it'd be 2 over 38. What's that? 0.05. Okay, so we need another decimal place. What was the 18 over 38? One more decimal place. 473. And one more decimal place on this. 052. Agree? So this is what we'd expect. If there's 18 reds and 18 blacks and 2 greens, then we'd expect 47.3% of the time we'd hit red, 47.3% of the time we'd hit black, and 5.2% of the time we'd hit green. Okay, now this is what we observed. So is this table rigged? Meaning, does it favor one of these colors more than it should? Okay, does it favor, say, red or green more than it should? So here's the trial. Here's the observations. Okay, so this is based on how many? 200 trials. So based on 200 trials now we're going to compute what would we expect in 200 trials. So we would expect, what, 47.3% of 200 to be red, and the same to be black, and then 5.2% to be green. So let's get those numbers. So this would be expected frequency. So 94.6. Is that right? We'd expect 94.6 of them to be red, 94.6 to be black, and 10.4. Thank you. To be green. Okay, and our observed was 88, 102, and 10. So let's use StatCrunch and do this. So this would be an easy one to do by hand because there's only 3 outcomes, 2 degrees of freedom. But let's practice using StatCrunch. I hope you guys wrote that down. Where's StatCrunch? There we go. So let's try it over here in variable 5. So let's do the frequencies. What were the frequencies for red, black, and so hopefully someone wrote them down. $88, 102, and 10. Okay, so that was our sample, and what do we expect? We said 90.6, 94.6, 10.4. Okay, so when we go to goodness of fit, I hope those show up as possibilities. Let's see here. Our observed was variable 5. Yes. Okay, so look. So now I put it in column 5. The observed is column 5. Expected. Oh, but the expected, I think they want. Let's just see what happens. They want it as percentages, right? This isn't going to work. Okay, remove this. There we go. Okay, this isn't right because this is, we need percentages here. Oh, God, this is the same thing. Okay, So I happened to open the window where this was already up, okay? So here it is, 0.4736, 0.4736, 0.052. Here's the observations. And so we want to go to goodness of fit, chi-square test. Observed is the O. And then P, the P column. And now here we go, compute. So chi-square 1.06. So we go to our chart. Two degrees of freedom, 5% significance level, 5.991. And what was our chi-squared value? 1.06. So clearly this is not rigged, right? So there's no evidence to suggest that the outcomes of the table are different than what we would expect, right? Because the chi-square was, here we are at 5.9, the critical value. Our data suggests a chi-square of 1.06, meaning there's no evidence here that this roulette table is rigged, okay? The data is consistent with what would we expect for a fair roulette table. Okay, so then I'll mention this, the loaded die question. So here's an example. The loaded die is where the numbers 1 through 6, what we'd expect would be the same percentage or the same probability for every outcome. So you wouldn't need a column for that in the StatCrunch. You would just use that button that said all the outcomes have the same probability, right? So all you would need to enter is the frequency of your simple random sample, and then when it asks you about, what are you expecting, then you just click on the little tab that says all probabilities are the same, and then it'll give you the chi-square number. Anybody have a question? Okay. Don't forget, homework will be in 2 separate sets on the online homework this weekend. Which one? 12.30. Make sure your name and the date is on your sheet. Name and date, please. Yeah.
I'll give you this for a tournament this week.
Okay.
It's at home, so it shouldn't really affect anything.
Okay.
I mean, it's here, so
right.
I'll be fine.
Good luck.
Thank you.